Okay, hello everyone, and welcome to this week's IDEA Series talk. Today we have a discussion brought to you by our own postdoc here at the Brown Theoretical Physics Center, Konstantinos. He's going to be talking about Cartan Integrable Systems with, I forget exactly the title, but it's with applications for supergravity.
Right.
And he's going to be starting right now with kind of a chalk talk type presentation, so take it away.
Cool, thanks. Hi everyone. Let me share my screen. Can everybody see?
Yes, we can see that.
Yeah, okay, great. So the goal of this talk is to demonstrate the use of a piece of mathematics called Cartan Integrable Systems and their applications to various supergravity theories. The motivation behind this is that higher dimensional theories like supergravity or string theory often demand the presence of various higher rank P forms. For example, 11-dimensional supergravity demands a 3 form. And not only that, but depending on the specific value of space-time dimensions, various dual descriptions may or may not exist. So for example, in 10-dimensional supergravity, one can use either a 2 form or a 6 form, but such a duality does not exist for 11-dimensional supergravity. So hopefully I will use Cartan Integrable Systems to explain this behavior in a cleaner way. And given the nature of our meeting, I want to give a minimal but self-contained description. So if you allow me, I will very quickly review some material to make sure that everyone is on board. So the experts, please excuse me. And if you have questions, please ask anytime. So we'll start with a review of Lie algebras, Lie groups and Lie algebras. Then we go to Moore-Cartan equations. And then I will introduce the generalized Moore-Cartan equation and the definition of Cartan integrable system. And then we'll talk about trivial and non-trivial Cartan integrable systems and their relation with cohomology classes. And then hopefully at the end, we'll have enough time to do application to 11-dimensional or even 10-dimensional supergravity. So if everything else fails, the message that I want you to take home is that there is a thing called Cartan integrable systems and provides a straightforward way to find non-trivial extensions of Lie groups when such extensions exist. Okay, so let's start with Lie groups, Lie algebras. So as you know, a very nice way of visualizing Lie groups is as group manifolds, meaning that you have a surface, and at each point on the surface you associate a group element, and all these group elements are parameterized by a set of labels. I call them Y here. So at this point you have the group element G of Y, and at this point you have G of W, and maybe over here you have the identity, which is another group element. And all the group elements which are continuously connected with the identity can be expressed using the exponential map as exponentials of YA, TA. And those TAs are just the tangent vectors in the identity point, and they form a basis in this tangent space. And they are the generators of the algebra, and they satisfy the usual this relation. And the C's are the structural constants of group G, and they're not just arbitrary constants because they have to satisfy the Jacobi identity, which is as this form. And therefore, for these structural constants, it provides this constraint when you can square bracket means antisymmetrization of all the indices. So now that you have these group elements, you can multiply them. So you have the group multiplication. You can multiply this group element, for example, over here with this group element over there. That maybe give you another group element over here. And it will be parameterized by a set of labels. But now these labels will be functions of, will be a function of W and Y. And now since you have this composition map, you can find how the coordinates themselves change under the group action. So if you do a group transformation parameterized by group element, by group parameter epsilon, then your new coordinates will be this f of epsilon and y. And if you assume that epsilon is small, you can Taylor expand the usual Baker-Campbell-Hasdorff type of equation. And thus, one can write the transformation for these coordinates in a very compact way by introducing this lowercase t, which is a first order differential operator. And these coefficients here, e, a, n, they just give you the change of the mth coordinate in the 8th direction. Okay, so all that is known and straightforward. Now, of course, the lowercase t objects, they generate the action of the group on the coordinates. So in a way, they provide a representation of the group. So they better satisfy the group algebra. And that means that this A and this E coefficients are not arbitrary, but they have to satisfy this constraint. And this constraint can be written in many different ways. I will massage it a little bit to write it in a way which will be convenient later. And I will do that by multiply with the inverse of E from the right and various integrations by part. And then you'll find that the same equation can take this form. Where these E, N, A objects are now the inverse of the E that we had previously. Okay, so this is all the everything I wanted to remind you from Lie group theories and Lie algebras. So we had, using the coordinates, we had a basis, and we can find a new basis using this E, which of course can be understood as a frame in the language of differential geometry or gravity. But now one can consider dual bases. So go to the contangent plane. So the dual versions for the partial coordinates are the differentials, and the dual basis for t's, I'll call them sigma. And of course, these sigmas can have a can be expressed in the coordinate basis using some coefficients, which, as it turns out, is the inverse of the e's, the things we have found previously. And this can be seen from the duality, as you know, that the duality between these two objects means that by calculating this combination, you get a delta AB. And if you feed in the definition of lowercase t and sigma, you'll find that these E's are indeed the inverse of the E's we had above. So all these are straightforward manipulations. But now, since we have a one form, we can calculate this exterior derivative. So let me do that very quickly. So this will be dyn wedge dym parcel n EMA, and then you anti-symmetrize the NM because of the wedge, and you have a 1/2. But this combination is exactly the expression we found here from the closure of the Lie algebra. And therefore, once you substitute here, you'll find that these sigmas, they satisfy this equation, which is the Mare-Cartan equation. And the Mare-Cartan equation is nothing more than the closure of the Lie algebra, but from the viewpoint of the dual one forms. And you can see that being expressed by the fact that these C's are the structure constants of the group G. But then if you recall that these C's are not arbitrary, but satisfy the Jacobi identity. So you may ask how you recover this constraint from this viewpoint. And the way you find it is through a consistency condition, which is the fact that d square of sigma must be 0. So you act with an exterior derivative from the left, so you get dc of sigma plus 1/2 d of sigma a, sigma b, ABC is 0. So this first term is trivially 0. So it better be that this combination is 0. And in fact, it is precisely because of the Jacobi identity. Okay, so this is the well-known Mare-Cartan equation. And there is another way of rewriting that is by defining this sigma without indices. This is a Lie algebra valued one form by contracting with the generator of the algebra. And for this sigma, the Mare-Cartan equation takes this more familiar expression like this. Now this equation can be solved. There are two solutions. I can write two solutions. I'll call the first one sigma right, which is G inverse dg. And this other one, I'll call it sigma left, which is minus dg G inverse. And of course, G is the group element that we had previously. It is straightforward to check that these are solutions of this equation. And just as a additional information, I'm not going to comment on that. This solution, the sigma right, can be used to construct covariant derivatives for group G, and this solution sigma left can be used to construct group transformations. And also, as you may understand that this Mare-Cartan equation is very restrictive. The coordinate dependence of sigma is completely fixed, and there is no wiggle room for dynamics at all. So you can imagine that as the vacuum configuration in the Lie group picture is you have a global Lie group, and then once you want to introduce dynamics, we usually gauge that group. And this notion of gauging can also take place from the viewpoint of one forms by relaxing the sigmas. I'm not going to go over that, but this is how you introduce the curvature tensor, find its Bianchi identities and the covariant derivatives is straightforward manipulations. All that. So let me give you a simple example of how you go from the algebra to the More-Cartan and back. Let's consider the very simple, the one-dimensional supersymmetry algebra. So the one-dimensional supersymmetry algebra has two generators, one translation. There is no indices because there is only one direction, and the supersymmetry transformation. And the algebra is very simple. P commutes with P commutes with Q, and Q, the end commuter of Q with Q will give you, let's pick a normalization, minus 2P. And then to find the More-Cartan equations, as we said, you usually, for each generator, you introduce a one form. So the one that corresponds to P, I'm going to call it E, and the one that corresponds to Q, call it psi. And then since we know the algebra and the structure constants, you can immediately write the More-Cartan equations. And this is what you get. So it's very easy to go back and forth. All right, so this is all I wanted to review from More-Cartans and Lie groups. So now let's introduce generalized More-Cartan equations. So the advantage of viewing Lie groups from the More-Cartan viewpoint is that it immediately suggests a generalization. And this generalization is, what if instead of having a set of one forms, we get a set of higher P forms? So I'm going to denote these forms as thetas. They're labeled by some index A, and they have a rank that may depend on this index A. So another one would be theta B with rank PB, and so on. So given this set of higher forms, then one can write generalized More-Cartan equations, meaning equations of this type. So the exterior derivative of one of these forms, and then you write sums of products of thetas. So an example would be, you have some set of constants here. These are the analogs to the C's that we saw previously. And then you have theta B1, P1 wedge, theta B2, P2 wedge dot dot dot, theta Bn, Pn is equal 0. This is a generalized More-Cartan equation. And the generalization is in two directions. Not only we went from one forms to higher forms, but also we allowed for a product of more than two terms. Because if you recall, in the More-Cartan equation, you had the product of two one forms. Now we can have the product of n forms. So this is a second direction of generalizing the More-Cartan equations. Now, of course.
Oh, sorry, Konstantinos. Yes. So here in this generalized equation, is the value of n is it related to the p form, the rank of the p form?
Well, it is related in the following way, which I'm going to explain right now. That in order for this equation to make any sense, you need to have some consistency conditions, and the one consistency condition is that the left-hand side here is a p+1 form. So p+1, it must be equal to p1 plus p2 plus dot 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 pn, meaning that this set of constants, which depend on how many indices you have, they must be non-zero only for the thetas that satisfy this condition. So another way to address your question is that, let's say I have a set of 1 billion thetas. not all products will participate in this generalized Moré-Cartan equation, but only the ones that satisfy this. So we'll take, let's say, the product of three terms, let's say a 2 form, a 5 form, and a 10 form. So only in those cases this equation makes sense. Is that does this answer your question?
Yep, that's perfect. Thank you.
Yeah. Okay. And of course, the second consistency condition is that this generalized Moré-Cartan equation has to be consistent with the fact that d square of a must be 0. So again, this constrains this set of constants C and forces on them some notion of generalized Jacobi identity, which looks like this. Oops, excuse me. B1, B2, Bn, desymmetrized A is equal to 0. So this is a generalization of the Jacobi identity. So if someone gives you, if somebody gives you a set of thetas that satisfy this generalized Moré-Cartan equation, and they are consistent, meaning these consistency conditions are met, then this defines what we call a Cartan integrable system. This is the definition of Cartan integrable system. Okay, so let me give you a couple of examples of Cartan integrable.
Can I ask real quick?
Please.
Is there, so if we can we translate back to the like vector field, like the tangent space picture, is like can you go back from the forms to say anti-symmetric tensor field or vector fields, say on, and I was just wondering, is there kind of the geometric structure you have?
Yes. Yeah. I
don't know if you're going to go over that later. But
right. Yeah. No, I'm not going to comment on that. And in principle, yes, but you'll see that you have to go beyond vectors. You have to go to tensors.
Exactly. Yes. Yeah.
Exactly. Right. And that's why viewing this from the point of one forms, that generalization is straightforward because you go from one forms to p forms. Versus the other case, you have to include all kinds of crazy PQ tensors, which may not be obvious.
I see. Okay, thanks.
Yeah. Yeah, examples. Let's do an example. Let me give you a set of thetas. Theta 1 is a 1 form, and theta 2 is a 2 form now. And let me give you a set of generalized Moré-Cartan's equation that they satisfy. So this is the set of Moré-Cartan equations. And the question is this a Cartan integrable system? And you have to check whether these consistency conditions are met. And the first one is obviously met. And for the second one, you have to check that d square on theta 1 is 0, which obviously is from the first equation. And then for d square of theta 2, you have to calculate. So let's do it very quickly. So you act with another d from the left, you'll get a term d theta 2 wedge theta 1. And then there's another term where the d acts on the theta 1, but this is trivially 0 because of the first equation. So I'm not going to write that down. And then you substitute the d theta 2 rule. And this is theta 2 wedge theta 1 wedge theta 1. But this is trivially 0 because the wedge product of a 1 form with itself is 0. So indeed, this is a Cartan integrable system. Let's do a slightly different example where now we use fermionic 1 forms. So let me have a fermionic 1 form and a fermionic 2 form. And they satisfy this set of generalized Moré-Cartan equations, wedge lambda 1, wedge lambda 1, And the question is this a Cartan integrable system? And again, the answer is yes, because you can trivially see that the d square on either of those is 0. So this is a consistent system, therefore it's a Cartan integrable system. Now that we defined what the Cartan integrable system is, I want to distinguish between trivial versus non-trivial. And this distinction is the following: is if a Cartan integrable system is equivalent to a set of More-Cartan equations, then we will say that this Cartan integrable system is trivial and specifically is equivalent to a group G that generates these More-Cartan equations. So this big tilde symbol is for to display the equivalent notion between the, and to make this more clear. So given a generalized, Cartan integrable system, that means someone gives you a set of thetas. They satisfy the generalized More-Cartan equations. So you have some constants and theta, wedge theta, dot, dot, dot. Theta is 0. And then d square of theta is 0. On the other hand, on the other side, we have a group G, which means somebody provides a set of structure constants, which can be, let me use a different label, can be used to write More-Cartan equations for one forms. Now, in order for these two to be equivalent, and thus for the Cartan integrable system to be trivial, we mean that these thetas can be constructed out of the sigmas. Specifically, that there are constants such that these thetas, let's say this P form, are P polynomials of the sigmas. And if you find such constants where the thetas can be constructed out of sigmas, and using the More-Cartan equations, you can reproduce these generalized More-Cartan equations, then your Cartan integrable system is equivalent to the group G, and we call that trivial because it doesn't include any more information than the More-Cartan equations. And then you can also imagine that the non-trivial Cartan integrable systems are the ones which are not trivial, and therefore the thetas cannot be constructed out of the sigmas. Okay, so let's check these definitions on the example that I gave you previously. So previously we had the theta 1 and theta 2, and we said that this is a list, not an undercommutator. So we said that d theta 1 is 0, d theta 2 is theta 2 wedge theta 1. And the question is this, we check that this is a Cartan integrable system. So the question is this a trivial one? And the answer is yes, because one can find a set of one forms, let's call them sigma 1, sigma 2, which satisfy this set of More-Cartan equations. And we can define theta 1 as sigma 1 and theta 2 as sigma 1 wedge sigma 2. And with these definitions and these More-Cartan equations, you can reproduce this set of generalized More-Cartan equations. So therefore, this Cartan integrable system is trivial and equivalent to the group which is responsible to this set of Moré-Cartan equations. And having the Moré-Cartan equations, you can immediately find the group. As we said, for every one form, you introduce a generator. So these two, and then from the Moré-Cartan, you can read off the structure constants. T1 with T1 is 0, T2 with T2 is 0. The only non-trivial one is T1 with T2. In this case, the coefficient is -2 T2. So this is the group which is equivalent to this Cartan integrable system. Now let's talk about non-trivial Cartan integrable systems and their relation with cohomology classes of the group G. So the question I want to ask is, how many, if we start with a group G, which means someone is providing a set of sigmas, one forms that satisfy the Moré-Cartan equations, how many, if any, non-trivial Cartan integrable systems can I find? And the answer would be related with the cohomology classes of group G. So let's see how that goes. So given this set of sigmas and their Moré-Cartan equations, if one can find a p+1 form constructed out of sigma, by the way, this symbol, if it's confusing to you, it's a Greek shorthand notation for omega. Instead of writing all that, just write a circle with a line under it. Okay, so if you can find a p+1 form called omega, which is constructed out of sigma, there is a set of coefficients here, and it's a p+1 polynomial of sigma, p+1, such that the exterior derivative on omega of sigma is 0, which is, we call it closed, and omega of sigma cannot be written as an exterior derivative of a p form constructed out of sigma. I mean, you find the coefficients here. So this lambda is a p polynomial sigma. So if you can find an omega which is closed but not exact, these two conditions defined what we mean by cohomology class. Specifically, this is the p+1 cohomology class, and is usually denoted as H with capital uppercase index p+1 cohomology class of the group G, and with this notation. So if you can find such an omega, which is an element of the p+1 cohomology class, meaning it's closed but not exact, then this omega is a perfect candidate for the right-hand side of a generalized Moré-Cartan equation, and forces us to introduce a new, I want to emphasize that, a new p form, let's call it A, which satisfies this generalized Moré-Cartan equation. And before you ask any questions, you may, I want to emphasize the new character, and by that I mean that the AP cannot be constructed out of sigma. If one can construct A out of sigma, then omega from this equation obviously will be exact and therefore not an element of the cohomology class. Okay, so the distinction here is that A is a new object that you must introduce. And then you take this newly found A and you put it in your list of forms. And now you see we went from a group to a non-trivial Cartan integrable system. And the non-triviality boils down to the fact that A is new. And then you repeat. In this Cartan integrable system, if one can find a form, let's call it W, a Q plus 1 form constructed out of sigma and A, such that it's closed but not exact, then one is forced to introduce a new form which satisfies this generalized Cartan equation. And then you put that into your list of objects and repeat until you exhaust all possibilities. So the lesson here is by studying the cohomology classes of your group, meaning finding all forms which are closed but not exact, you can find non-trivial extensions of your group to Cartan integrable systems. And in fact, there is a theorem that one can prove that all possible ways, all possible non-trivial Cartan integrable systems that one can construct starting from a group G is into one-to-one correspondence with the size of the cohomology classes. And not only that, but the notion now of triviality when a Cartan integrable system becomes trivial becomes more clear. In fact, let me phrase it in a different way. So we said we start with a group G. We managed to, following this procedure above by studying the cohomology classes, we find non-trivial Cartan integrable systems. But then one can ask the question, okay, can I find an extension of my group? So can I find a new group which includes G, such that the non-trivial Cartan integrable system that I found over here becomes trivial with respect to this enlarged group? So one can ask this question, and this question translates to the fact that so you have G, which is a set of one forms. You go to G tilde, which is a bigger group. So in addition to these one forms, you add new one forms. So in order for your Cartan integrable system to become trivial under this group, that means that the new forms that we found previously, now they can be constructed out of sigma and sigma tilde. So if that's the case, then our Cartan integrable system will become trivial under this enlarged group. And you see that that means that your omega p plus 1 forms become exact. So they drop out of the cohomology because they can be written out of like this. And the same for W. All right. So I think that's all the information I needed. And now we can go to applications to supergravity, unless there's a questions that will be.
Can I ask a quick question?
Please.
So, so I get that, like, this procedure of extending systems that come from, like, Cartan systems that come from groups to these generalized Cartan integrable systems by looking at the structure of the cohomology classes that's a way of constructing these Cartan integrable systems. But is it true that every Cartan integrable system can be constructed in such a way?
That's a good question. So the Cartan integrable systems I was talking here are the ones that have a, their core have a resemblance with some group G. So which means that you can play this game. So you're asking about Cartan integrable systems that include there are no one forms at all. So I'm not sure about the answer there, but I think there are two theorems proven by a mathematician called Sullivan, and he classifies all possible non-trivial Cartan integrable systems, and I think he proves that you can always associate them with some underlying group. So I think the answer is the answer to your question. I think the answer is yes. All non-trivial Cartan integrable systems can be constructed in this way.
Okay, thanks.
Can I just clarify real quick? So these kind of this A and B forms here, these new ones you had to introduce.
Yes.
So you aren't, they're still on the same underlying kind of manifold, right? You're not kind of enlarging, right? So, because at the end of the day, we started with some group manifold, we looked at one forms, and now we're adding other higher forms to construct this generalized algebra. And I just want to make sure that, right, that this AP here is just some other P form on that manifold on G.
Correct. Correct.
Okay.
Yeah. The notion here is because that there is a non-trivial cohomology in your group. That means that your one form is not a complete basis. So you have to add new elements, and in this case, this P form.
I see. Great. Thanks.
So let's do applications to supergravity. Okay, so the supergravity, the 10-second introduction to supergravity is a theory of gravity plus supersymmetry. And the 2-second introduction to supersymmetry is that this is a property of a theory where the theory remains invariant under the exchange of bosons to fermions and fermions to bosons. And of course, the number of bosons must match the number of fermions. Oops. Now, the construction of supergravity, at least the vacuum configuration, the global group, is the super Poincare group. And the super Poincare group, of course, it includes the Poincare, so it has the translations and the rotations, and then the super part comes from the supersymmetry. And then let me quickly remind you the algebra. So rotations with rotations gives you rotations. Rotations with translations give you translations. Rotations with supersymmetry give you supersymmetry. Translations, they commute. Translation with supersymmetry, they commute. And supersymmetry with supersymmetry give you translations. And the gamma that I wrote here, this is the gamma matrix, is a generalization of the Pauli matrices, and you need to include, if you have spinors, you need to include this object. And if for a second I turn on the spinorial indices that I have over here, you see the left-hand side is, because it's an anticommutator, it's symmetric in the indices. Therefore, this gamma object must also be symmetric in these spinorial indices. And since we have a group, we have a Lie algebra, we can immediately write the More-Cartan version of this algebra. So as we did for every generator, we introduce a one form. So for the translation, this is the frame. For rotations, this is a spin connection, and for Q, this is a psi, a fermionic one form, which is called the gravitino. And as is typical for any theory of gravity, the spin connection is not an independent field, but can be expressed in terms of frames and the gravitino in this case. And so you can write the More-Cartan equations for the super Poincare group, and they have this form. As you may recall, the structure constants of the Poincare algebra is just eta metrics and deltas. So this is exactly what you get here. For the frame, you get this, and also another contribution coming from the supersymmetry part. And for psi, this is 1/4 AB wedge gamma AB psi is 0. And also, if you recall, I mean, this is the definition of your curvature, 0 curvature. This is the definition of your covariant derivative of psi. And this is also this part is a covariant derivative of the frame. All right, so this is a translation of the Poincare, super Poincare to the More-Cartan description. Now, let's do 11-dimension supergravity. Okay, so we fix space-time to be 11. And let's quickly, oh, I needed a new page. So we fix space-time to be 11. And let's do a quick count of bosons and fermions. Okay, so for bosons, we have the frame. So I will turn on all the indices now. So it's a one form that carries a flat index A, has diffeomorphisms, has Lorentz symmetry and all that stuff. So if you take all that into account, you'll find that it carries 44 bosonic degrees of freedom. And for the gravitino, it's a one form, which is a spinor as well. And if you do the counting, is 128. So obviously there is a big mismatch. So you cannot even write a supersymmetric theory. So the only thing you can do is add new fields, and then you play around of how many fields, what type of indices carry, what kind of symmetries these indices have, and all that. And then you'll find a possible solution is to introduce a new form, a 3 form. It's a gauge 3 form, and therefore carries, you count the degrees of freedom is 84. And then, therefore, if you add all the bosons, you'll find 128, which matches the fermionic degrees of freedom, therefore, at least is a reasonable starting point. But from the point of view of the algebra, there is no way that you can see here a 3 form appearing. So you wouldn't guess that, right? But this is where Cartan Integrable Systems shine, because out of your set of one forms now, one can find a 4 form omega, which is basically, if I recall, I don't remember the coefficient, but it's psi bar gamma AB wedge psi wedge EA wedge EB. This form is constructed out of psi and E. You can prove that this is a closed form. This is based on the More-Cartan equations I wrote above, and also various properties of these gamma matrices, which are called Fitts identities. And you can also prove that this cannot be constructed out of is not equivalent to the exterior derivative of a 3 form constructed out of psi and E. Therefore, we have a non-trivial element of the fourth cohomology class of the super Poincare group, which means we must introduce a brand new preform which satisfies this Moore-Cartan, generalized Moore-Cartan equation. Great. Now, this is a very straightforward justification why you need the three form, because there is a non-trivial extension of the Poincare to a Cartan integrable system. Now, you can ask the question, okay, can I find an extension of an enlargement of my super Poincare group such that this non-trivial Cartan integrable system becomes trivial? And the answer is yes. I'm not going to give you the detail. I'm just going to give you the answer. The answer is that you have to introduce a bunch of one forms. This is what enlarging the group means. Introduce new generators, therefore new one forms. So you introduce a one form that carries 2 antisymmetric indices. You introduce another one form that introduces 5 antisymmetric indices. And also you introduce a new fermionic one form. And if you do that, then this new three form that you found here from the non-triviality of the cohomology now can be completely constructed out of psi e, the B2, B5, lambda. So this non-trivial Cartan integrable system becomes trivial for this enlarged group. And we can find what that group is because we have the one form, so we can translate back to the generators, to the generator picture. So for each one form, I introduce a generator. And these generators will modify the super Poincare algebra that I wrote previously in this way. So this is the super Poincare I wrote previously, and the modifications you get by these new generators are these ones.
So
please.
Yeah, so I'm a little so these new one forms, are they related to the original bosonic and fermionic one forms, or do they have their own complete? They have their own complete unique algebra.
They are new one forms. They have their own Moore-Cartan equations that mixes with the psi's and the e's, but they're independent one forms. And the thing that makes this new Cartan integrable system trivial now is because the three form we discovered previously can be constructed out of the all these one forms. If we didn't have the B's and the lambda, we couldn't construct the A3 form, and that's why we discovered it above as a Cartan integrable system, and we had to add it. But now we enlarge the group, we introduce new generators, therefore new one forms, these ones, and by doing that, they carry their own Moore-Cartan equation. And by doing that, we can construct the three form out of these objects.
Awesome, thank you.
And now I'm just writing the modification because we go from a group G to a bigger group, which of course includes G. So this is what we had previously, and this is the extension. And for this commutators, you also find modifications. And for a second, let me turn on the spinorial indices in the first equation. So as I said, the left-hand side is symmetric in the spinorial indices. Therefore, everything on the right-hand side must be symmetric on the spinorial indices. This first term is symmetric and is the usual supersymmetry algebra we had. And these other pieces are the only 2 other gamma matrices you can add that are symmetric in the spinorial indices. So even if you haven't done any Cartan Integrable System description, you may have guessed these contributions because of the symmetry or antisymmetry of gamma matrices. But you have never would guess the presence of a new spinorial generator, which is not supersymmetry, something else, because the anticommutator of eta with eta is 0, doesn't give you translations. So it's an additional fermionic charge that your theory must carry. And this is the full group structure underlying supergravity. Now, if I have a few more minutes, or if there are questions, you can ask me here, or if I have a few more minutes, I can talk about the duality and maybe 10-dimensional supergravity. So are there any questions?
I just want to mention a few people have dropped out because I guess they had a commitment at 1 o'clock, but I'm happy to stay around.
We can okay, if you want, we can stop.
I'm happy to hear the extension, but if anyone wants to leave, this is a good point to ask a question. Yeah.
All right, in that case, I'll continue. I need like 5 minutes maybe. So every time you have a theory that demands a form, in this case a 3 form, you can construct what's called you can take its curl. So you can construct the field strength. For example, for the photon, you have a vector and you can construct F mu nu. This is the object that carries the physical degrees of freedom. And when you construct the field strength F, then you can do a duality and go to F star. In this case, we're in 11 dimensions, so you're going to use the 11-dimension epsilon symbol. So you're going to get a 7 form. And if you have a 7 form, you can find its potential, which is a 6 form. So you would think that, oh, because I have a 3 form, I can replace it with a 6 form because they carry the same degrees of freedom, the same information. But this is not the case in 11-dimension supergravity. And I'm going to show you this to you in 2 ways. The first way is if you manage to construct the Lagrangian of 11-dimension supergravity, which is complicated, but one of the terms is the 11-dimension epsilon, F for this object, F for A3. So you see that this A3 in this term appears naked, bare. So that duality procedure will not work. Now, in order to find this this answer, you have to construct the full Lagrangian, which is very non-trivial. This answer can immediately come out of Cartan Integrable Systems, because we had the psi and the e, and then we found that we needed 3 form. So let's continue. We didn't finish the program, right? So can we construct any close but not exact forms using all these 3? And the answer is yes. You can construct a 7 form, which depends on psi, e, and a3. And it has an expression. I'm not going to write the expression because lack of time. But the point is that this is closed and not exact. And therefore, it forces you to introduce a 6 form, which satisfies this generalized Mori-Cartan equation. But now you see, in order to define this, to find this object which forces the introduction of the 6 form, I need to have the A. I cannot replace. I need to have the 3 form. I cannot replace the 3 form with a 6 form. If I don't have the 3 form, then this object does not exist. So the duality procedure will not work in 11-dimensional supergravity, and that immediately follows by finding that this 7 closed but not exact form, which depends on A3. Now, this is in contrast with 10-dimensional supergravity. So 10-dimension supergravity, this term in the Lagrangian that I wrote, because we are in 10 dimensions, it immediately drops out because it's using the 11 dimension epsilon. So it's no longer there. So you don't have a bare free form anymore. So in principle, you can do the duality. And in fact, this will work. And you can see that from the Cartan Integrable System point of view, because you can find two independent non-trivial Cartan Integrable Systems. The one uses a two form, and the generalized Moore-Cartan equation is this one. And the other one uses a six form. Maybe that's more. I can write it. It's 1/2 psi bar gamma 5 psi with A1 A5. Oops, E A5 E0. So you see, I can independently define the A2 because this form is closed and not exact and depends on psi and E. And I can independently define the E6, A6, because this closed form and not exact it depends on psi and E. So I can find two non-trivial extensions, and they're related by the duality procedure I described previously, because in 10 dimensions, if you start with a two form, the field strength is a three form. The dual version, the star, is now you use the 10-dimensional epsilon is a 7 form, and the potential of that is a 6 form. So this is precisely that duality that you get here. So I think I'll stop there. Any questions or comments?
Yeah, can I ask real quick? So, I mean, it seems like this kind of Chern-Simons term is the problem with this duality.
Yeah.
So, I mean, can we see this in just like a regular 3D Chern-Simons? Is there some, if I try to do maybe a standard kind of Poincare duality in a Chern-Simons gauge theory in 3D, will it just not work?
Well, yeah, I mean, yeah, in general, if you have the bare potential in lurking in the Lagrangian, naively you will think that that duality doesn't work. Now, here, I gave it as a heuristic argument, and the full backing up of the statement comes from the Cartan Integrable System, which is straightforward. In that case, depending if you have some very, cleverly chosen theory, maybe something else happened. So I cannot give a general answer.
Sure. Yeah. I mean, in general, it seems like in low dimensions, there's probably not as many interesting examples of these Cartan integral systems, just because you have fewer forms available.
Oh yeah. That's why my motivation was for theories which can be defined in higher dimensions, like supergravity and string theory. So only in those theories you need higher P forms, which means the underlying symmetry is not a ordinary group algebra, but a Cartan integrable system.
Gotcha. Thanks.
Konstantinos, I just want to say thanks for this really nice talk. And I have one other question. So just going back to sort of like the general picture of Cartan integrable systems, it seems like this method for extending from groups to non-trivial generalizations of these Cartan integrable systems using, the cohomology classes. It just makes me wonder, like, can this only be done with Duran cohomologies, or like if you have, systems where, let's say, some of these sigmas are closed to begin with, it seems like it might be easy to construct some other nilpotent operators whose cohomologies you could study and potentially extend groups with. So I was just wondering if anybody's thought about that, or if that's something that you know about.
The answer is yes, somebody has thought about that. And in fact, the cohomology I was working here is not that Deram cohomology, is what's called the Chevalley cohomology, because Because you can, if you have, forget omega, let's go phi. If you have a P form, you can define is this D, the exterior derivative. So let me write it here. You can, the definition comes from the structure constant, not derivatives. And wherever I was writing generalized Moret-Cartan equations or ordinary Moret-Cartan equations, you had two terms, D of something plus terms equal 0. So you can take that as a definition of what D means. So in general, in this case, we have, so these are the structure constants of A1, A2, B, F, A3, AP plus 1, B. And then you have the sigma A1, sigma AP plus 1. So because of the Moret-Cartan structure, you can find that for every P forms that I used, this equation holds, and therefore you can take it as a definition of what the D is, and therefore you can forget that the RAM cohomology, which is based on the fact that two derivatives commute, now your cohomology is based on the structure of the symmetry structure of the structure constants, and this is called the Chevalley cohomology, because this is the Chevalley elliptical or exterior derivative. So this is a natural candidate for Moret-Cartan equations and their generalization, because you have the structure constant. Now, if you find some other structure which provides another candidate to play this role, then I guess you can construct the analog D and study its cohomology, and that will be the answer to what you're looking for.
Okay, thanks.